In this video, I'm doing a comparison of methods, the disk method with the cylindrical shells method. So first, let's take a look at a problem using the disk method. So we have this function, f of x equals 4 minus x squared, which is an upside down parabola. And so we're looking at the area between 0 and 2, which is where it would intersect the x-axis. And we want to rotate it around the x-axis. Rotate around the x-axis. So to use the disk method, we have the basic formula. The volume is equal to the integral from a to b of pi times f of x squared dx, where f of x represents the radius of the disk. So here's our sample rectangle. And so if we're rotating this around the x-axis, then the radius is going to be the height of the rectangle, where the height of the rectangle is the function value. So putting it all together, we have the volume is equal to pi times the integral from 0 to 2. And so we have 4 minus x squared dx. All right, so that's as far as I'm going to go with that, just setting up the integral. I want to make sure that you understand how you set up the integral based on the disk method. And so let's also take a look at this in Desmos. So if we go to Desmos, the first integral that you see is the one that I just set up. And the volume is equal to 53.61. Now let's go back and set this problem up using the cylindrical shells method. So we're going to set it up exactly the same way. So we're going to have, let's just say we got this here, and that's there, and that's there. Now we're rotating it about the x-axis. Okay, we're rotating it about the x-axis again. But using cylindrical shells, it is important to realize that the height of the rectangle is parallel to the axis of rotation. So the axis of rotation is horizontal. The length of the rectangle must be horizontal, right? And so we're rotating this around the x-axis this way. And so this distance here is going to be the radius. And so let's set up the integral. And let me get rid of all of that. So the basic integration problem is volume is equal to 2 pi. Now normally it would be xf of x, but we are now integrating along the y-axis, all right? Because this is now delta y, okay? The width of the rectangle is delta y. So we are integrating on the y-axis from 0 to 4. And so the radius here is not an x value. The radius here is a y value. So it's 2 pi y. And then the height of the rectangle, which is normally the function value. The function value is the height of the rectangle, but we now need to express the height of the rectangle, the function value, where x is a function of y. So we had y is equal to 4 minus x squared. So that means x squared is equal to 4 minus y, or x is equal to plus or minus, we're just going to go with the positive, square root of 4 minus y. So that would go in here, 4 minus y dy. So it's important to understand that when the rectangle is horizontal, that we are integrating it with respect to y. Because delta y is now, the width of the rectangle is a y value. It's delta y is a y value. And so we integrate along the y-axis, which means our function needs to be expressed in terms of y. Everything needs to be expressed in terms of y. Well, how do I know if this is correct? Well, we go back to Desmos. And I put that integral into Desmos, and what do you know? I get the exact same volume. So I did the problem two different ways, two completely different methods, and I checked them in Desmos, and they came out to be exactly the same. So the moral of the story is you can use a variety of different methods, and it should come out to be the same. And you want to choose the method that is the most appropriate. So which of these two methods is most appropriate? I don't know. The disk method was probably the easiest. Cylindrical shells was a little bit more work. It's going to be a little bit more work integrating this. You'll have to use U substitution, but it's not a difficult U substitution, but it is doable. So mostly I just wanted to show you how you can set these up in two different ways. So I hope that was helpful. Bye-bye.